Today we will teach you input element and signal processing elements, which is worksheet 3 of your electro-pneumatics notes. Okay, so this is the typical control chain you have learned earlier: input element, signal processing element, final control element, and output element. In the last lesson, we learned about output elements such as cylinders, motors. We also learned about final control elements such as directional control valve, flow control valve, motor contactors. So today, we will take a look at signal processing element and input element. Let's take a look at signal processing element first. Signal processing element is referring to the brain of the system. Okay, so examples we have given you all earlier are computers, microcontrollers, programmable logic controllers. Those are actually high computing power signal processing elements. Okay, so sometimes the application does not require you to use such expensive controllers. You can also use something cheaper, and yet they can serve their purpose as the brain of the system. Things like control relay, counter, or even time delay relay. Okay, let me give you an example on this. For instance, when someone enters the toilet, okay, the motion sensor will sense the person in the toilet. Then it will turn on the light. Okay, such simple application does not require you to use microcontroller or even a computer. You just need something as simple and as cheap as a control relay or even a time delay relay, depending on how you want your application to be like. So we will study this in depth later on, how to use a control relay and how to use a time delay relay. And of course, you can also use a counter depending on your application as well. Next, we will look at input elements. Okay, later on you will learn about how to draw a push button and what are the use of a limit switch. Okay, for now, maybe I just give you a head start. Limit switch is used to detect the position of the cylinders. For instance, how do you know that the cylinder is fully extended or fully retracted? The machine has no eyes. So what will replace the eyes of the machine is actually the limit switch. So you can actually use a limit switch to detect whether the cylinder is fully extended and fully retracted. This is just one of the applications of limit switch. Of course, there are many other applications for limit switch. Next, we will also learn about toggle switch, okay, and how to use them. You will also learn about proximity sensor, and as the name suggests, proximity means close distance. Okay, so there are two types of proximity sensor. One is an inductive and one is a capacitive. Inductive detects matter, capacitive is matter and non-matter. All these we will study in depth later on. There is also a type of sensors called photoelectric sensors, which uses light. Okay, there are 4 types of photoelectric sensors you will learn later on: fiber optic sensor, true beam, retroreflective, and diffuse reflective. Okay, so all these, don't worry, we will elaborate them later on and show you how it looks like. So you will also touch on a bit on ultrasonic sensor. Ultrasonic sensor basically you can see in your daily life. Okay, for instance, the reverse sensors of the car, okay, uses ultrasonic sensor. Well, the next thing you will learn also is pressure sensor, okay, and detent switch. Detent switch is just like your e-stop button you can find in trains. Okay, now we will take a look at the next page, okay, where we will learn how to draw the push button and the toggle switch. Okay, so let's take a look first. Okay, for a push button, okay, what are the applications? Okay, the application normally is used to start-stop a system. So you press the start push button to start the system, and you press the stop push button to stop the system. That's normally how we use a push button in machines. Okay, and how do I draw the symbol of a push button? Okay, so for symbol of the push button, this is how you draw a push button when it's normally open. Okay, so I will indicate over here, normally open. Okay, this is a normally open push button. Okay, what happens when you press this push button? Okay, so when you press this push button, normally open will become normally open, help close. Okay, let's look at how I draw this. You'll be on top of the contacts. Okay, so this is how you draw a normally open, help close push button. Okay, it's when you press the push button. You can see the line of action. Okay, next, how do you draw a normally closed push button? Okay, so for a normally closed push button, let me change my color of my pen. This is how you draw. The contact is actually below. Okay, so it's very important to show that it is touching if it is closed position. Okay, like for instance, you can see normally open, held, close. I will show that it's touching the contacts. Normally closed, I also show that it's touching the contacts. Normally open, I'll show that it's not touching the contacts. Okay, so when you press this normally closed push button, what happens to it? Okay, let's take a look. Okay, so imagine when you press this push button and your line of action is actually downwards, correct? So it will become open. Okay, and normally close, held, open. Okay, so I will just write down over here in case you wonder how to spell this. Normally open, held, close means, okay, this is how you held, close. Okay, and NCHO will be normally close, held, open. Okay, so you can see that this one is the activated, I will call this activated position. This one is the non-activated position. POS stands for position. Okay, so to revise again, this is the push button, normally open. If you press it, you'll become normally open, held, close. That means it allows current to flow through. However, if you are using a normally closed push button, okay, when you press it, you'll become normally closed, held, open. That means it breaks the circuit. Okay, and the normal positions are called non-activated position. The activated position means what happens when you press it or when it's activated. Okay, next, let's take a look at toggle switch. Okay, toggle switch normally is just an on-off selector. Okay, and they have a single pole, single throw, means something like that. This is also a toggle switch, or single pole, double throw. Okay, so I label this single pole, single throw, which you can see over here. Okay, and there are also another type called single pole, double throw, which is like this. Okay, okay, you can see that when you change it, this is called single pole, double throw. Okay, so when you switch, you switch to this contact. Okay, okay, sorry, accidentally deleted this. Okay, next, draw and connect a circuit to switch on and off using a toggle switch. Okay, wiring diagram. Previously, okay, what have you all been learning? Okay, you have learned how to draw battery to be this way. Okay, and then you have also learned how to draw toggle switch, right? Something like that. And if it's a light, it will be something like that. Okay, this is the type of wiring diagram that you have learned previously in EL Tech. Okay, however, over here we are going to draw ladder diagram. Okay, we call this electrical ladder diagram. Okay, it's just another representation. Okay, how the circuit work is still the same. So let me draw this. First, you always draw the power line, plus, okay, and negative. Okay, so this is a toggle switch. Okay, and this is the symbol of the light bulb. Okay, you always draw from input to output or final control element. Okay, depending on the question, or processing, signal processing element. Okay, depends on the application. In this case, they said that draw and connect a circuit using a toggle switch. So can you imagine that when you turn on this toggle switch, okay, power will pass through and turn on this light bulb. Okay, and it's very important in the electrical ladder diagram to label all your symbols So I'll label this 1TS, okay, the first toggle switch, and I'll label this 1LB, okay, the first light bulb, because depending on the application, there can be as many as 3 or 4 light bulbs, or even 3 or 4 toggle switch. So it's very important to label all your symbols, okay? Okay, let's proceed on to the next page. Draw and connect a circuit to switch on and off from a motor from 2 toggle switch such that both switches must be activated to turn on the light, okay? So we will have 2 toggle switch, okay? Again, for electrical ladder diagram, there must be a plus, okay? And there will be a minus, okay? Positive and negative. And I already told you input will start on the left, and then the signal processing or final control output will be on the right, okay? So let's take a look. So I will have 2 toggle switch and both must be activated. So it's an AND logic. How do you draw AND logic? Okay, let's take a look. First, I must have this first toggle switch. Okay, AND means together in series, right? So I'll have the second toggle switch too, because the question says 2 toggle switch. Okay, and then they will turn on a light. Okay, and I'll label this light 1LB. Okay, so can you visualize that when these 2 toggle switches are on, the light will turn on because current can go through? Now we'll take a look at the either or logic, where either one of the switches when activated will turn on the buzzer. So how do I draw the buzzer? Okay, the symbol of the buzzer can be drawn this way. Okay, I will label it 1BZ. Okay, 1 buzzer. So I will draw the electrical ladder diagram first, plus and minus. Okay, the question is either one of the switches when activated will turn on the buzzer. So I will draw the either or logic. Okay, how do I draw this? Take a look. First, when it's either or means that when you press 1TS, the buzzer will turn on. Okay, so can I draw this way first? Okay, and again, when you press the second toggle switch, the buzzer will also turn on. So I can draw this way as well for the second toggle switch. Okay, let's look at this diagram again. Okay, you can see that when you press the first toggle switch, okay, current will flow through the toggle switch and turn on the buzzer. Okay, and when you press the second toggle switch, current will flow through and turn on the buzzer as well. Okay, so you can see just now, as I indicated in green previously, that when you press either of the toggle switch, the buzzer will just turn on. So this is the either or logic. And in part A, this is the AND logic, because when you need to press these 2 toggle switch in order for current to flow through to turn on the light bulb. Okay, so with this, we will next learn about limit switch. And before we draw all the symbols for a limit switch, I will first show you how to use a limit switch on cylinders. As you can see, this is my double acting cylinder. I have limit switch 1 and limit switch 2. Limit switch 1 is used to detect the retracted position of the cylinder, and limit switch 2 is used to detect the extended position of the cylinder. Hence, as you can see, when the cylinder is extended, it will activate limit switch 2. Okay, and when the cylinder is retracted, it will activate limit switch 1. Okay, that's how you use limit switch for detecting positions of the double acting cylinder. Now we are back to the worksheet, input element, limit switch and sensors. So first, we will look at limit switch. Okay, limit switch is a type of contact sensing sensor. In other words, it requires the object to touch the sensor. Okay, in this case, it's the limit switch itself. So this is the schematic of the limit switch, and let's take a look at this application. So this is the conveyor system. So the goods are actually traveling from left to right. Okay, and the limit switch is mounted here. Okay, I can see that the purpose of this limit switch is to know that the goods has already arrived at this position, because when the good is at this position, it will activate this limit switch. Okay, and you can see that this goods needs to touch the limit switch in order to activate it. That's why it's called a contact sensing sensor. Okay, how do we draw a normally open limit switch? Okay, normally open limit switch can be drawn this way when it's not activated. Okay, means that not touching at all. Okay, so normally open. And there's another type of limit switch which is normally closed. Okay, this one we'll go through later. So let's focus on the normally open contact limit switch. As I already draw the normally open contact limit switch, what happens when it's activated? When it's activated, you'll become normally open, held closed. Okay, so because the line of action is from bottom to top, okay, meaning that when it touch, this will be at the bottom of the contact. Okay, and it's touching. So it become normally open, held closed. Next, let's take a look at the normally closed limit switch. Okay, so if you are having a normally closed limit switch, this is the symbol of it. Okay, and you can see that the contact is actually on top. Okay, the contact point is actually on top. Okay, so normally closed, when you activate it, it become normally closed, held open. And again, as I said, the line of action is from bottom to top. Okay, for the symbols, so it will become like this, and it's not touching. So normally closed, held open. Okay, several things to take note. Okay, first you must be able to notice that normally open, held closed symbol is not the same as normally closed symbol. Okay, and same things goes for normally open comparing with normally closed, held open, even though they are both open. Okay, so to summarize, we have two types of limit switch, normally open and normally closed. Okay, if it's normally open, when you activate it, you become normally open, held closed. If it's normally closed by default, when you activate it, means that the object touches the sensor or the limit switch in this case, you'll become normally closed, held open. Okay, with this, let's go to the next page. Okay, where we'll talk about contactless sensing. Okay, contactless sensing means that the object is not touching the sensor, okay, or vice versa. So there are many types of contactless sensing. Okay, we are just having three types here. First is the inductive sensor. Okay, inductive sensor, capacitive sensor are both proximity sensor. Means that they need to be mounted close to the object, but they do not need to touch the object. Okay, so inductive sensor is used to sense matter. Capacitive sensor is used to sense matter and non-matter. Okay, or even liquid. Okay, and there's also another very commonly used type, photoelectric sensor. Okay, which uses light. Okay, to sense the object. So what are the advantages of non-contact sensor? Means that the sensor does not need to touch the object. Okay, well, very obvious thing is the object to be sensed is not disturbed. Okay, because you're not touching it, so you're not disturbing it. So this enables lightweight object and those with delicate surfaces to be sensed. Okay, and there are a lot of advantages of non-contact sensing. Another important one is no mechanical moving parts means longer service life. Okay, so just like if you look at the limit switch, which is a contact sensor, okay, it has mechanical moving parts because the object needs to touch the limit switch, okay, in order for it to be activated. So it has a shorter service life, okay, for the limit switch in that case. So I'll leave it for you to read all this, and you need to know as well that non-contact sensing also have its disadvantage, okay, because you need to tune the sensor, okay, and you need to install the sensor such that there's minimum environmental disturbance as well. Okay, so with this, we will go on to elaborate on the different type of sensors. We will now take a look at classification of sensors, whereby in the industry there are two types, AC sensor and DC sensor. AC sensors uses AC power source. For instance, in Singapore, our VAC voltage is actually 220 volts. Okay, so this is how you wire up a AC sensor to a AC power source. And most of the time, you can find that in most machines we are using DC sensors. Okay, there are three types of DC sensors: 2-wired sensor, 3-wire sensor, and a 4-wire sensor. Okay, so 2-wire sensor is pretty straightforward to wire. 3-wire sensor is what you can find in our lab, and sometimes we even have 4-wired sensor, okay, where you can configure whether is it used normally open or normally closed. Okay, so for our syllabus, we will focus on 3-wire sensor, whereby there are 3 points. Plus goes to the positive of the DC power supply, negative goes to the negative of the DC power supply, and this will goes to the load. Okay, so let's take a look at the next page on the different types of sensors that we have. We will now look at classification of sensors by application. Basically, we are looking into these two areas, proximity sensors and photoelectric sensors. Proximity sensors means that the sensor must be mounted close to the object in order to sense. Okay, so there are mainly 2 types of proximity sensor. One is a capacitive sensor and one is an inductive sensor. So let's take a look at the capacitive sensor first. Okay, capacitive sensor, you need to mount as close as 20 mm from the object, okay, in order to sense. So what is typical application? You can detect liquid between tin and non-metal wall. Okay, so if you mount, take a look at this diagram. If you mount a capacitive sensor here, it can actually detect the liquid inside, okay, provided the container is a tin and non-metallic wall. It can also be used to detect metal and non-metal objects, meaning it can detect the presence of an object. Next, we will take a look at inductive sensor. Inductive sensor is used to sense matter, and it can be mounted as close range up to 8 mm. Okay, so as you can see in this diagram, this is the inductive sensor. It's trying to detect this metal cap over here, and it needs to be mounted very close to it in order to sense. Okay, so inductive sensor is used to sense matter. Okay, one typical application that you can see in our daily life for inductive sensor is the inductive loop sensor that is mounted underneath the road. Okay, so let's take a look at the following slides on how does an inductive loop sensor works and how is it being mounted. Okay. Earlier on, we learned about inductive sensor, which is used to detect the presence of matter. So now we will look at one commonly used application of inductive sensor, which is this induction loop sensor, okay, or we call it an inductive loop traffic detector. Okay, basically it just consists of an insulated loop of wire that is laid in the cards above, as you can see in the image. Okay, so whenever a vehicle passes over this loop, right, it will create a disturbance in the current, okay, and hence this inductive loop sensor is able to sense the presence of a vehicle. Okay, with this information, the traffic light control system can then control the traffic lights more efficiently and effectively. Okay, so if you want to know more information of how inductive loop sensor can help in controlling the traffic light, you can actually go to this website and take a look. And you can even watch a video to see how the workers cut the loop, okay, and prepare the box and lay the cable. And this second video shows how they actually seal up the loop, okay. So the next time you pass by any traffic light junction, you will see this inductive loop sensor, and you will know that it's not just mere markings. It is a sensor over there to detect the presence of a vehicle, so that the traffic light control system can control the traffic light more efficiently. Let's take a look at photoelectric sensor now, whereby there are 3 different types of photoelectric sensor listed here: true beam sensor, retroreflective sensor, and diffuse reflective sensor. So for true beam sensor, is made up of a pair of sensors. One will transmit the light and one will receive the light. Okay, so if there's no object over here, okay, no object, this receiver will receive the light from this transmitter because there's no object blocking the path of the light. Hence, it can know that there is no object sense. However, if there is an opaque object, okay, the keyword here is opaque because only opaque objects can block the path of the light. then this receiver will not receive any light from this transmitter because all the lights has been blocked by the opaque object. Hence, it senses that there is an object presence. So this is how true beam sensor works. The sensing distance can be up to 5 meters, meaning that this pair of sensors can be mounted as far as 5 meters. Okay, again, this is just a guideline. Different manufacturers will have different specifications, so it really depends on your application as well. You may not need up to 5 meters, maybe 1 or 2 meters is good enough. So they do have models of true beam sensor that is up to 1 meter, 2 meter, and so on and so forth. Next, let's take a look at retroreflective sensor. As you can see this diagram, this is the sensor and this is the reflector, okay? And in between the sensor and the reflector is the object, okay? So how does retroreflective sensor works? Let's take a look at this diagram over here, okay? Basically, I just enlarge this diagram and draw it in a simpler manner. So this is the retroreflective sensor, this is the reflector. So if there's no object, the sensor will just shine the light on the reflector and reflect back the light. So the sensor knows that there is no object because it is able to sense back the light that it has emitted. However, if there's an opaque object, okay, in between the sensor and the reflector, like in this case, okay, it will block the path of the light. Hence, the sensor will not sense any light at all. So in this case, it knows that it has detected an object, okay. The sensing distance will be shorter. For retroreflective is up to 1 meter. Again, this one depends on the models you have purchased. So as a guideline, we put here 1 meter. Okay, lastly, let's look at diffuse reflective sensor. Diffuse reflective sensor is even simpler. You don't even need a reflector. Basically, it's just one sensor. Can you see this diagram over here? This is the sensor, and it's being used to sense an object, okay, in this application. So if I enlarge this diagram over here, this is the diffuse reflective sensor and this is the object, okay. So if there's an object presence, this sensor will shine the light, okay, and the object will reflect back the light. So it senses that the object is present. However, if there's no object, okay, this sensor, whatever light it has emitted, will never be reflected back. Hence, it knows that there is no object if there's no reflected light back into the sensor. Okay, TX stands for transmit, RX stands for receive. Okay, this is just a notation. And diffuse reflective sensor is normally used to detect colors, whether it is smooth or rough surface, because the smoothness and roughness of the surface will affect the light, right? And whether the thing is reflective, and mainly is used to detect opaque object. Another important thing to take note about diffuse reflective sensor is we will not use on applications whereby we need to detect black color objects. Okay, so imagine this is a black color object and this is the diffuse reflective sensor. So whatever light that this sensor is shining on this object will get absorbed by the black color. Okay, so hence this sensor will not receive, okay, the light that is being reflected by the object. So it will not be able to detect that the black color object is there. Okay, hence we should use sensors such as retroreflective sensor, true beam sensor, or even capacitive sensor to detect black color objects. So you can see that different type of application will require different type of sensors. Now we shall take a look at this web page, okay, from Omron, which actually shows you the different type of sensors that we have went through, okay, like for instance photoelectric sensors, okay, proximity sensor, ultrasonic sensor, so on and so forth. Okay, the rest you can actually read up for your general knowledge. Okay, for photoelectric sensor, you can see that this web page actually shows you the 3 different types of photoelectric sensor: true beam, retroreflective, and diffuse reflective. So for true beam sensors, it's always a pair because it needs an emitter and a receiver. For retroreflective sensor, it's only one sensor itself, emitter element and the receiver element is being inbuilt, okay, and of course you need a reflector. So the next time when you purchase a retroreflective sensor, you will expect to have a sensor, okay, which is the retroreflective sensor itself, and a reflector, because you need a reflector to reflect back the lights, as it uses the principle of sensing object interrupts the light. So if there's no object, it means that the light can be reflected back to the sensor easily. However, if there's an object, okay, it interrupts the light path. Lastly, they also talk about diffuse refractive sensor. Okay, so diffuse refractive sensor, again, it looks very similar to retroreflective sensor because the emitter and the receiver element is being inbuilt. Okay, however, it does not need any reflector at all. The object itself is like the reflector. Okay, so the sensing object will reflect back the light. So with this, you can also see the advantages of the sensors, okay, the features, and why photoelectric sensors are commonly used. You can even know the operating principles, okay, behind photoelectric sensors. Okay, so all this, I will leave it for you all to read out on your own. Now, let's go back to the worksheet. Okay, so the next page, we will summarize the type of sensors we have learned so far. So far we have learned about inductive sensor, which is used to detect matter, capacitive sensor, detect matter and non-matter, or even liquid levels, true beam sensor, retroreflective sensor, diffuse refractive sensor, and fiber optic sensor, okay, which we did not elaborate earlier on. So fiber optic sensor is actually another type of true beam sensor, except that it uses fiber optics. Hence, what's the key difference? It's used to detect tiny objects. Okay, so it's still a pair of sensors. One will transmit the light, one will receive the light. It's just that it is fine. Okay, hence it only detects tiny objects. Okay, unlike true beam sensor, whereby it can detect big objects. Lastly, we also talk about ultrasonic sensor. So ultrasonic sensor, the common application will be the reverse sensors of the cars, okay, or even sometimes it's mounted at the doors so that it can detect the presence of a vehicle or a human, and then it will automatically open or close the door. Okay, with this, we will take a look at the following pages to see the different type of applications and which sensor should be deployed for that particular type of application. Now we shall look at case study 1, whereby figure 1 shows an inspection station for pack cartons. So this is the pack carton, and they are being transported on a conveyor. This is the conveyor, okay. Name a suitable type of electrical sensor to be used at A, okay, to detect if the carton is present, and another at B to detect if the staplers are present. Okay, so let's look at sensor A first. So what type of sensors can be used? Okay, so I would suggest that we can also use capacity sensor, because capacity sensor can sense matter or non-matter. So in this case, we are trying to sense the box, so capacity sensor can do the job. Okay, other than capacity sensor, can we use any other type of sensor for A? I can also think of using retroreflective sensor. Okay, or even true beam sensor to detect the presence of this object. Okay, can I use diffuse refractive sensor? Well, I will try not to use diffuse refractive sensor because I do not know the color of this carton. So if it's a black color carton, diffuse refractive sensor may not work well. So because black will absorb light. Hence, I will choose either capacitive, retroreflective, or true beam sensor. Can I use ultrasonic sensor? No, I can't use ultrasonic sensor. The reason is because ultrasonic sensor, it's just a sensor itself, and it will detect, it will actually transmit ultrasonic wave. So if you mount an ultrasonic sensor at A, you will end up constantly detecting the conveyor and a lot of things around it. So ultrasonic sensor is not applicable for sensor A. Okay, now let's take a look at sensor B. It's used to detect whether staplers are present. Normally staplers are metal, right? So I would use inductive sensor. Okay, because inductive sensor can sense matter. Will I use capacitive sensor? No, I will not, because capacitive sensor will also detect non-matter. It may end up detecting this box if I use a capacitive sensor. Okay, hence it's best to stick to only inductive sensor to detect the presence of matter on this box. Okay, so let's take a look at case study 2. In case study 2, it says that bottled drinks transported on a conveyor are being checked at an inspection station before the outgoing station. So this is the bottled drink and it's going out of the station. Name a suitable type of electrical sensor to be used at each of the following points. P to detect opaque plastic bottle. Okay, so P I will use to detect opaque plastic bottle. Q to detect the liquid level. Okay. R to detect the aluminium foil. Okay, so let's take a look at the easiest one first. Detect liquid level. Okay, we have learned that capacitive sensor is best at that. Okay, so I'll use capacitive sensor to detect liquid level. How about R? R is also very easy. Aluminum foil, metal. So inductive sensor. And now I'll take a look at P to detect opaque plastic bottle. Actually, there are quite a few answers for P. Okay, one of the answers can be true beam sensor. Okay, another answer can be retroreflective sensor. Again, do you want to use diffuse reflective sensor? No, I will not, because again, I do not know the information of the color of this bottled drink. So I will not use it. And finally, any other sensors? Well, actually you can also consider using capacitive sensor as well. But since Q is also using capacitive sensor, so I will not try to use two identical sensors, okay, in a application. So I'll stick to these two answers. With this, we shall go to case study 3. In case study 3, we look at figure 3 here. So IC chips are being transported on a conveyor to be inspected by the sensors. Okay, IC means integrated circuit. Okay, so this is the integrated circuit chips. Okay, and M is used to detect the notch here, which is very small, and N is used to detect the number of leads that you have. So it's used for counting purposes. So a lot of students, when they see the word metallic leads, they will say, okay, the answer will be inductive sensor. Well, in this case, it's not true. We cannot use inductive sensor. Why? Because, take a look, we are required to count the number of leads. If we use an inductive sensor, okay, and you know that the pitch between the leads are very fine, the inductive sensor will not be able to detect the gap between the leads. Okay, so for such fine applications, right, we need to use fiber optic sensor. So M and N, we will use fiber optic sensors, okay, because as we learned earlier, fiber optic sensor is used to detect fine objects. Okay, they are just like true beam sensor, except that they use fiber optic cables and hence they can detect fine objects. Okay, next we look at case study 4. So in case study 4, they have this material transporter which perform path tracing. That means it will move along this track. Okay, this track can be a S-curve, or because this is just an illustration. So they mount a sensor on this transporter, which is used to detect a person or a machine that is within a distance of 20 cm to 1 meter. So what sensor should we use? Okay, a very obvious answer that come into my mind will be the ultrasonic sensor. Why? Because ultrasonic sensor will emit ultrasonic wave, right? So any object that come within this radius, okay, for instance, this is the object, okay, the sensor will sense and then it will stop. So the answer for this will be ultrasonic sensor. Okay. Okay, with this, we will look at the next page, which we will study control relay. Okay, now I'm showing you a website that actually has animation on how relay works. Okay, so the picture I'm showing you now is a basic relay because it only has one contact. So this is a single pole, single throw because there's only one contact. Okay, as you can see, when the coil has no power, this one will be open. However, when there is power going to the coil, as you can see now, it will close. Okay, so this is a basic relay. What I'm interested to show you is this single pole double throw relay. Okay, as you can see over here, this one is a single pole double throw. Okay, because it has two throws, normally open and normally close contact. Okay, so when there's no power to the coil, it's at normally close. As you can see, okay, when there's no power to the coil, the contact is at normally close. However, when there's power to the coil, means that the coil is being energized, you can see that it will switch to normally open. Okay, and you can make use of relay to turn on lamps, okay, or any other things that you want. And hence, relay is a signal processing element because you are able to control this relay to switch to whatever logic that you have designed for your application. Okay, so in this case, when the relay has been energized, you will turn on lamp B. When the relay is not energized, okay, you can see later on, okay, now the lamp A will turn on. Okay, so that's how relay works. And a relay, to summarize, made up of two components, the coil and the contact. Now we shall take a closer look at the control relay. And I would like to illustrate the schematic by drawing a single pole double throw control relay over here for you to understand better. So this is the control relay. A control relay will make up of coil and contacts. So I'm drawing a single pole double throw control relay. So I will have one coil, okay, and then it has double throw, means it has two positions, okay. So okay, I will label this A, B, C. Okay, A, B, C is the contact. Okay, so how does this work? Let's take a look. So when there is no power to the coil, means that there's no voltage difference across the coil. Okay, means that it's off. Okay, let me spell out properly. Okay, so what happens? The contact will remain A to B. Okay, meaning that current will flow from A to B. So A to B is actually a normally closed contact. A to C is actually a normally open contact. Okay, hence when the coil is energized, okay, which means that it's on, the contact will switch. It will switch from A to B to A to C. Okay, this is how a control relay works. Okay, so next, let's take a look at the application of a control relay. So one of the main application is to turn on several devices at the same time. Okay, this is one. The second is small signal to turn on a big signal, okay, for safety reasons. Okay, I will go through this application in detail with the following example below. Okay, for now, you must know how to draw the symbols of a control relay. So you can see a control relay is made up of two parts. One is the coil, one is the contact. Okay, so again, the symbol will also make up of two parts: the coil, okay, and the contacts. Okay, they have normally open, and remember to label the contact, okay, because this contact belongs to the coil 1 CR, so you have to label the contact as 1 CR, and normally close. Okay, so now let's take a look at how to do the following example. Design a ladder diagram to turn on off 3 light bulbs simultaneously when a toggle switch is activated. Okay, again, when you draw ladder diagram, draw the plus first and the minus. Okay, so remember I always said that inputs will start from the left and signal processing, final control output will be on the right. Okay, so let's see the flow of this diagram. So you are saying that when the toggle switch is activated, we are supposed to turn on the light bulb, okay, using control relay. So how are we going to do that? First, when you press the toggle switch, okay, this is how you draw the toggle switch, and remember to label, it's very important. You're supposed to energize the control relay, right? So you have to energize the coil of the control relay. I call it 1 CR. And then when the coil is being energized, we need to turn on the light bulbs. Okay, light bulb is the output, so output should always be on the right. Okay, so you ask yourself, who should turn on the light bulb? Okay, it should be the contact, right? So let's visualize how this works first. When you press this toggle switch, this coil will be energized. When it's energized, normally open will become closed and the light bulb will turn on. Okay, with this, I will continue to draw for the 3 light bulbs. Okay, there are many ways of drawing this. One simple way is to do this. Okay, you can just continue to write 1 CR and the second light bulb. Remember to label. Okay. Okay, let's see how this circuit works first. Okay, which I'm going to draw in green to show you the current path. So when you press the toggle switch, current will flow from positive to the coil to energize it. Okay, so this coil is now energized. Okay, when this coil is energized, if you draw normally open 1 CR, it will become closed and the current can flow through to turn on the light bulb. Okay, and the same thing goes for the second light bulb. Because the coil has been energized 1 CR, the contact will also close. Okay, and the light bulb will turn on. Okay, so this is how it works. Okay, and then let's look at the scenario when the toggle switch is not closed. So when the toggle switch is not closed, 1 CR will be off, means that the coil is not being energized. Because it's not being energized, whatever you draw will stay there. Okay, so if you draw normally open 1 CR, it will stay open. Okay, and the light bulb will be off. Okay, as you can see, because no current can pass through the normally open contacts. Okay, other than this diagram, you can also do a shortcut to simplify this diagram. Okay, into this way, positive, negative. I have a toggle switch here. Okay, it's supposed to turn on the control relay. Okay, and when this contact close, it will turn on 3 light bulbs. Okay, this is how you draw. And remember to label. Okay, so either method is correct. As you can see over here, I draw my light bulbs in parallel, and it's very important to know why it is drawn in parallel, because in parallel it means that the voltage across the bulb is the same. Okay, so we cannot draw light bulbs in series. If we draw the light bulbs in series, like in this example, let me draw and show you. Okay, so if I draw the toggle switch here first with the control relay, okay, and I draw the light bulb in series, Okay, this is wrong. Okay, why? Because if you draw light bulbs in series, what it meant is the voltage across the bulb will reduce, correct? So you will not be able to light up this light bulb at all. Hence, we cannot draw outputs, signal processing element, or even final control element in series, okay, because of the resistance. Resistance in series means it will add up, and hence the voltage will start to drop across each light bulb. However, in parallel, it's different. The voltage will still maintain at 24 volts in this case, because my power supply is 24 volts across each light bulb, and hence it will ensure that the light bulb will turn on when the control relay is being activated. Okay, so now I'll erase this because in the first place you're not supposed to connect the outputs in series. Okay, we will look at this now. Design a ladder diagram to switch on a 100 volts light bulb when operator press a switch at the 24 volt DC circuit. Okay, so let me erase nicely and take a look at what exactly it meant. Okay, so this application is actually what I have mentioned earlier, small signal to turn on a big signal for safety reasons. Okay, so the operator will press the switch at 24 volts. So this is 24 volts power supply. Okay, and this is negative. Okay, so this is the switch, toggle switch is always on the left, okay, because they're inputs. Okay, so when I press the toggle switch, I will energize this control relay, okay, 1CR. Okay, and then I will also have a 100 volt power supply, okay, directly tied to the contact of the control relay, okay, in this example, and it will turn on the 100 volts light bulb, okay, I call it 1LB. Okay, so why is it safer? Because when the operator press the toggle switch, it is only at 24 volts, okay, but however, at the control relay contact side is already tied to 100 volts. However, the user is not touching the circuit at the 100 volt side. The contact relay is directly connected to the light bulb. Hence, it is safer. Okay, so let's visualize in green how this works. When you press the toggle switch, the control relay will be activated. Hence, when you draw normally open, it will become closed, and 100 volts will pass through for the light bulb to be on. Okay, so that's what we meant by small signal to turn on a big signal for safety reasons. Okay, with this, we'll go to timer relay. Okay, so a timer relay is just like a control relay, okay? But the main purpose is to generate delay. Okay, so two important things to take note also for the symbols. One is the coil and another one is the contact. Okay, so how do we draw the coil for timer relay? So we will always label the coil first, and this time round we will write the timing, okay, of the delay, maybe 5 seconds. Okay, I just give you an example. And how to draw the contact of a timer relay. Okay, so this is the normally, it's like a stickman, normally open. Okay, you have to label 1TR. This is normally open, and they also have the normally close, okay, which is on top of the contact. Okay, so this is the normally closed position. Okay, with this, let's take a look at the next example. Design a ladder diagram to turn on the light bulb 5 seconds after a toggle switch is pressed. Okay, so to design this, it's not difficult. Okay, first, let me pull out the pen. Okay, you need a positive and a negative. Okay, so again, as I said, inputs on the left, signal processing, final control, and output elements are always on the right. So we are trying to make use of a time delay relay over here. So in this example, it's something like this. When the toggle switch is being pressed, 5 seconds later, the light bulb is on. Okay, so this is like a flow of the sequence that's going to happen. So first, I'll draw the toggle switch. Okay, the toggle switch will have to energize the coil of the timer delay relay to generate a delay of 5 seconds. So this is the coil of the time delay relay, and remember to label 1TR with a 5 seconds since the question says that. Okay, and we only label at the coil side. Okay, so next, 5 seconds later, the light bulb will turn on. So I should draw normally open or normally close. Well, the answer is normally open because 5 seconds later, then the contact will close to turn on the light bulb. Okay, so this is how the circuit looks like. Let's visualize in green for how the current is going to pass through the circuit. Okay, so when you press the toggle switch, this timer delay relay will be activated. 5 seconds later, okay, this contact will close and the light bulb will turn on. Okay, what happens when you release the toggle switch? Okay, the moment you release the toggle switch, okay, this is what's going to happen. 1TS will be open, the coil will not have any more power. Since you draw a normally open contact, it will stay normally open, and hence the light bulb will be off. Okay, now I would like to give you another example, okay, using push button. Okay, so this is the new scenario I'm going to give you right now. Okay, where you can see a push button is being connected to a time delay relay of 10 seconds. And I tie the normally open contact of the time delay relay to a light bulb and a normally closed time delay relay contact to the second light bulb. Okay, so what happens when the one push button is pressed continuously for only 6 seconds? Okay, let's take a look, and I'm going to draw in green to show you how the current is going to flow. So when the push button is being pressed, okay, current will flow from left, okay, which is the positive, okay, to the time delay relay. But because it's only being pressed for 6 seconds, this coil will not be activated, okay, because it needs 10 seconds for this coil to be activated. Hence, if you press push button for only 6 seconds continuously, and you let go of a finger after 6 seconds, you will not be able to energize this time delay relay. So what happens to the light bulb then? Okay, so let's take a look. What happened is a normally open time delay relay, because the coil is not energized, will stay open. Hence, the first light bulb will still be off. Okay, how about the second light bulb? Well, the second light bulb will remain on. Why? Because this time delay relay is normally closed. Hence, if your coil is not being energized, if you draw a normally closed contact, it will stay closed. Hence, the second light bulb will be on. With this, we have covered EP3, which we will learn about the input elements like the different type of sensors, inductive, capacitive, the different type of photoelectric sensor like true beam sensor, retroreflective, diffuse reflective, and so on and so forth. And in the last two examples, you learn about signal processing elements, for instance the control relay and the time delay relay, which we will use extensively later on in EP4.